All right, the derivative. Let's talk about derivative today. Now, at its very simplistic terms, derivative is, most of us know by a rule that if you have a function, f of x equals to x raised to the power of n, and if I ask you derivative, it is represented by f dash x. So this becomes n times x raised by n minus 1. We know that, right? All of us. But let's take a step back and understand what this is to start with, right? This is the straight application. But what exactly is derivative? Derivative is nothing but, before derivative, we need to understand there's something called rate of change. You would have heard this word quite often, the rate of change. What is rate of change? A rate of change of y or f of x with respect to the change in x. How my y value changes with respect to my x value. The most commonly used word for rate of change is the slope or the gradient, popularly known as n. It tells me rise over run, rise over run. What is rise? Y2 take away y1 over x2 take away x1. What is y2 minus y1? Change in y. What is x2 minus x1? Change in x. How y is changing as x is changing is what the rate of change is, or slope is all about. Simple. So now if I have to find the rate of change between 2 points, let's say I have a line like this, a curve like this, and I say there are 2 points, x1, y1, x2, y2. And I ask you, what is the rate of change between these 2 points? For that matter, let's say I take this line off and I say, okay, there are two coordinates, which are x1, y1, x2, y2. Give me the rate of change between this. Oh, that's fine. Join them. Join them. And the slope of this line is the rate of change. Change in y with respect to change in x. y2 minus y1 over x2 minus x1. That's slope or rate of change. I said, that's fine. What if still we've got 2 points, x1, y1, x2, and y2. But this time, it's not a straight line. This time, it's a curve. And I ask you, give me the rate of change between the 2 points. All right, that's fine. Join the dots. You still join the dots and you find the slope of this line again. y2 minus y1 What? X1. Easy peasy. Awesome. So far, so good. I now also start calling this as not only rate of change, because rate of change, I know I've been calling it for a while, but when I have a curve which is not a straight line, which is not linear, it's non-linear, and I need to know the change between the 2 points, I call it as average rate. I use the word average rate of change. So now if you're given a curve and you're asked to find the rate of change between any 2 points, it is very simple. Draw the 2 points on the curve, join them with a straight line, and find the slope of that straight line. That is the average rate of change between the 2 points. I don't care about the curve. Just join the 2 points with a straight line. A very important terminology that needs to be understood here is called, in geometry, there's a word called secant. Secant is a line which cuts the curve on more than 1 point. Secant cuts the curve more than 1 point. And there's also something called tangent. Tangent is that line that touches is the word, that touch the curve at 1 point only. So right now, this line, which is cutting the curve at 2 points, and we are trying to find the we're trying to find the slope of that line, is the secant. So far, so good. Everyone's fine, right? I'm just going very conceptually so that you'll start making sense when you see the question, right? Now, let's draw another scenario. Let's say the x. Let us say the curve is something like this. And I ask you, all right, let's try to find the rate of change between these 2 points. How do I find it? You say, that's super easy. Just join them, y2 minus y1 over x2 minus x1. So you found the average rate of change between the 2 points. This point is x1, and this point is, let us say, the other point x1 is h units away from x1. So what is this point? x1 plus h, right or wrong? Am I making sense? So if I have to, and let's say this is f of x. So what would be this value? This value is f of, or basically I just call it as x1. Let's say x1. And this point will be here f of x1 plus h, right or wrong? So far, so good. So what is the rate of change? Rate of change is, scroll maybe a little up. So my rate of change, my average rate of change, I say ROC is y2 minus y1 f of x1 plus h minus f of x1 over x1 minus x1 plus h, right or wrong? Which when I open the brackets up becomes f of x1 plus h minus f of x1 over, this will cancel when you open the brackets up. And this, or probably let's not do the algebra around it. And we say, oh, sorry, I think this should have been the other way around. My bad. This should have been x1 plus h minus x1. Sorry. So when you open the brackets up, you open this bracket, x1's gone, and eventually you're left with h. So that is the slope, which is m, of this red line, which is now written in y2 minus y1 over x2 minus x1 form. All good. We are getting it, right? You're soaking it in, right? Cool. Now, I now tell you that let's start to decrease the value of h. When I start to decrease the value of h, what will happen to this point? This point will start to come closer to x1, right? Because I'm decreasing the distance between the two. Correct? So let's say I halved h1, the h. So now your new point has come here. You've moved this point to this point. Why? Because you have halved the distance between the two. And now I ask you, find me the rate of change between this point x1 and this new point, because now I have decreased h. So what will you do? I'll say, all right, that's fine. Again, draw a line connecting the 2 points. And again, let's say this value is the new h. I end up finding the average rate of change and I will get the same answer here, with this new point being my y2 and x2. So far, so good. I will still end up getting the same value. Not a problem. Now, I say, and hear me out loud and clear. Now I say, decrease h to such an extent that it approaches zero. It is a super duper small value. What is h? H was the distance between x1 and, should I say, the other point was x2. So far, so good, right? So what will happen? And I'm saying, see, I'm not saying at any point in time that h is zero. No, because if h becomes zero, the 2 points will coincide. Then the concept of rate of change does not exist, because it's just 1 point when the moment h is zero. But if I say h is approaching zero, there's also a word called tends to. H tends to zero. The old school terminology when I was you was h tends to zero. Now it says approaches zero. So they use interchangeable. And what could be, what could be this value looks like? I mean, for example, h is 0.00000000000001. It is that small. It is that small, which is approximately zero, not zero still, right? I will not draw the graph, this one, I'll draw this graph again and I'll show you how it looks. Let's draw in the same color, red. That's the curve. That is where my original x1 was. And I'll change the color to find where is x2 when the distance is so small, literally almost on top of each other, where this value is x1 and this value, which is kind of looking still at uh, like x1, is x1 plus h, but h is approaching 0, right? Now I ask you, find me the rate of change between the 2 points. And you'll say, hang on, whenever I was trying to draw, whenever I was trying to find the rate of change, I used to just connect the dots and I used to find the slope of that secant. Secant was the line that connects the curves at 2 points, and I used to find the slope. I will still be doing the same. This is no different. Let me draw that secant. So that secant could be, maybe I'll change the color of my pen to find secant. I'm not happy with this. Could be. What is happening here? What is this a secant anymore from the normal pair of eyes? It is still touching 2 points, but with naked eye, it starts to appear as a tangent because it is touching the curve at 1 point now. Technically still 2 because h is not 0. But naked eye tells me it's a tangent. The 2 points are so close that I can just say they're 1, but they're still not 1. So what happened was that I brought these 2 points so close, I made the distance between the two so close that secant now becomes tangent. And I'm doing the same thing again. I need to find the slope of this tangent. Let me find it again. The slope of this tangent M is f of x1 plus h minus f of x1 over h. But I will say limit h is approaching 0. I've just told I've just told you mathematically that this h is not a normal h anymore. It is a super small value. So I have to mention it. And this is not average rate of change anymore. Average rate of change is when the two points are at a finite distance from each other. But here, the 2 points are with naked eye more or less 1 point. But technically, they are not. And hence, I call it as instantaneous rate of change. Or I also call it as derivative. What is this derivative? This derivative is also the slope of what? The tangent, not the secant. Slope of the tangent. Where is that tangent drawn? At a point. Where is that point? On the curve. So, derivative is also called the instantaneous rate of change, is also called the slope of the tangent at a point on the curve. At a point. Naked eye, 1 point. But technically, there's still 2. Because it looks It's one point. I say slope at a point on the curve. This is nothing but derivative. I'll give you a very real life example as well. This was all mathematical. Let's say you're driving a car, right? A very real life example. You're driving a car and you started from point A to point B. You started at, let's say, 10 a.m. You reached another point at 12 p.m. and you covered 100 kilometers. I ask you, what is the rate of change? At this point, let's say you started at t equals to 0. So this must be t equals to 2 because you're 12 p.m. Distance here is 0. Distance here is 100. So this point has the coordinates of 0, comma 0, and this one had 2, comma 100. So if I ask you what is the average rate of change between the 2 points, you'll say y2 minus y1 over x2 minus x1. 50 kilometers per hour is my average speed. That is what distance, what in the world of distance time, slope is called speed, right? Kilometers per hour. Change of distance with respect to change of time. Cool. So 50 kilometers an hour was the average speed. But now if I ask you, were you driving from time t equals to 0 to times t equals to, till time t equals to 2, bang 50 kilometer, your speedometer did not move at all? No, that was not the case. You would have accelerated, the traffic signals might be coming in, you would have halted a bit and you would have slowed down, picked up, blah, blah, blah. But average rate of changes is bothered about one point to the other, draw a straight line, find the slope. That's about it. That's average rate of change. But in your driving, in your car, there is something called speedometer, which is showing you the speed. That is derivative. It is showing you the instant speed at the time when you looked at it. So your speedometer is the derivative, the real life derivative in front of your eyes. That tells you instantaneous rate of change at the time you looked at it. At the time you looked at it. So if I'm on a highway and it's 80 kilometers an hour, and I just looked at my speedometer and it says 78. 78. At that time, when you looked at that instant, when you looked at it, it gave you the derivative, 78 kilometers an hour. So that is the real life example of the instantaneous rate of change, which is your speedometer. All right. I'll go another step down and let's try to take with now algebraically, how do I find the derivative? This way of finding the derivative, this is called the first principle. And questions can come in the exam to find the derivative using first principle. This is the first principle where you apply limits. And the stuff that we started at the start, here, this one, here, this is the shortcut version of first principle that helps us save time. Let's take an example and then I will finish this topic as in from a concept standpoint and we can practice. So now let's take an example. Let's say my f of x is x squared. We'll take a very simple example. My first principle told me that my derivative is limit h approaching 0 f of, and I'll not use the x one now, I'll just replace it with a regular x plus h minus x over h. We just talked about it. Let's try to find the derivative if that's my function. So I will say limit h approaching 0, f of x plus h. So can I say x plus h square? Take away x square over h. Let's just solve it algebraically. So I get limit h approaching 0, x square plus 2xh plus h square minus x square over h. A plus b whole square is a square minus plus 2ab plus b square. That's what I've just done here, just in case. I can cancel x square, and this becomes limit h approaching 0, 2xh h square over h. I cannot apply limit right now. I cannot sub in 0 here because limit actually tells you to sub that value in, right? It's so small, sub it in. But if I sub it in, h is in the denominator, it'll make function, it'll make derivative not defined. So is there a way I can get rid of this h from the denominator? Yes, I can factorize it. And I say limit h approaching 0, and I take h common, say 2x plus h over h. H gone now. So what's remaining? Limit h approaching 0, 2x plus h. Now I can sub in 0 here, and eventually my derivative becomes 2x. Now let's come back to our shortcut. My shortcut at the start when I kicked this topic off was if f of x is x raised to the power of n, then f dash x, the derivative is take this power down and reduce this power by 1. Let's see, we've achieved the same thing now. My f of x was x squared. N is 2 here. So my f dash x tells me, get this 2 at the front and reduce this 2 by 1. And what do I get? I proved my first principle. This is the shortcut of the first principle. And this is what